Hello, Science 9. This is some enriched content for you here. So if you're finding it's enough to just keep up with the regular content, just skip this lesson altogether. Okay, but if you are planning on skipping ahead and taking Chemistry 11 honors, or if you really think you might want to take Chemistry 11 honors, um, even in your grade 11 year, this is some really good stuff that will definitely help you out with that. Okay, and we are going to be looking today at how bond structure affects melting point. If you want your own copy of this document to write on, it's currently in the Schoology files, but I will also post it on Teams as soon as I've finished making this video, okay, in the enriched content section. Okay, so since we're looking at bonds, let's review for ourselves the three types of bonds. Okay, and those are, pause the video and see if you can remember for yourself what the three types of bonds are. Okay, if you could not remember, one of the types of bonding is ionic, and that is when we have a metal plus a non-metal, or possibly we might have some polyatomic ions in there as well. But it's definitely between a cation and an anion. Second type of bonding is covalent. And covalent is when we have a non-metal plus a non-metal. Okay, and the third type of bonding is where we have metallic bonding. And that is when we have a metal and a metal. Okay, ionic bonds result in ionic compounds. Covalent bonds result in covalent compounds, and you've been learning about naming ionic compounds and covalent compounds. Metallic bonds don't form compounds. Metallic bonds, either this can just be within a pure metal, okay, and gold, okay, if you have pure gold, 24 karat gold, or it could also be in an alloy, okay, in an alloy. So an alloy is something that it's a mixture of metals. So stainless steel, for example, is an alloy. It contains iron and chromium. At any rate, that's just a quick little review of what all the types of bonding are called and what they are between. We're going to look today at how the bond structure affects the melting point. First of all, what is melting point? Melting point is defined as the temperature at which a solid object will transition to the liquid phase. Now, how does a solid turn into liquid? Some form of energy, in the form of heat, okay, is needed to break the bonds that hold the solid together. Okay, and if a substance has stronger bonds, you're going to need to apply more energy. We need to apply more energy to break the bonds. And if we need to apply more energy, that means the temperature will have to be higher. Because we're going to have to apply more heat. And that means that the stronger the bonds are, the higher the melting point. Okay? What makes a bond strong? All right, so remember that positive and negatives are attracted to each other. Those are supposed to be arrows. I don't know. Maybe I'll just get rid of that and put in some. Man, my drawing's really bad today. There we go. Okay, so we have an attraction between a positive and a negative, and that is known as the electrostatic force, or it can also be known as the Coulombic attraction. So electrostatic force, electrostatic attraction, Coulombic attraction, those all mean the same thing, and they are all that attraction between positive and negative. These forces are stronger when the distance between the charges is smaller. Okay? So we could write that another way. We could say that the electrostatic force is proportional to 1 over the distance. It's inversely proportional to the distance. So the force, F, will get smaller as the distance gets bigger. And if any of you have done any of the math around this, it actually goes as the square of the distance, but we're not going to get too excited about that. You do not need to know this formula. All you need to know is that as the distance gets bigger, the force between the particles gets smaller. As the distance gets smaller, the force between the particles gets bigger. Okay, so it's an inverse relation. We could also graph this, okay, as the distance, d, between the particles, between the charges, I guess I should say, between the charges gets bigger, the force between the charges gets smaller. Okay, and it's actually a curve, but if you were to draw a straight line, that'd be okay because we're not too worried about the actual quantities in grade 9. Okay, second thing, Coulombic attraction is stronger not only when things are closer together, but also when the amount of charge is greater. So the more the charge, the bigger the force. So that is a direct relationship. Bigger charge equals bigger force. So if we were to graph charge, which is also represented as Q, okay? If we were to graph the amount of charge versus the force, okay, as the amount of charge gets bigger, the force gets bigger. So if we have a 2+ charge, that's going to exert a stronger force than a 1+ charge. If we have a 6+ charge, oh my gosh, that's like hugely stronger than a 1+ charge. Okay, for the purposes of this worksheet, oopsie, that arrow's pointing the wrong place. There we go. For the purposes of this worksheet, any charge greater than 1 is considered large. Any charge less than 1 is considered small, just to simplify our lives. Okay, and we're just going to review for ourselves what the heck is happening in an ionic bond. Okay, so this is our ionic bond. Remember, what kind of things does it occur between? That would be your metal plus non-metal, and we will end up with an ionic compound. Okay. Ionic bonds are formed when a metal ion sheds its outer shell valence electron. That would be like this one right here. Okay. And in order to fill the shell of a nonmetal atom. See how we have a nice little gap over here? All right. So sodium gives its electron to chlorine. And what that leaves us with is a sodium plus, Na plus, and a Cl minus, so that's a +1 charge and a -1 charge. And then we have that electrostatic force. What's the other word for electrostatic force? Coulombic attraction. Oops, there's a U in there. Coulombic attraction between the metal and the nonmetal ions, between the cation and the anion. Now, if you look at the space between these, the space between the ions is small. And if the distance between the charges is small, that means the strength of the force between them is going to be strong. So if the distance between the ions is small, the force between the ions will be large. Okay? Ions are generally small, so the distance between the ions is small, so the force between them is large. Also, for the purposes of this worksheet, remember we were saying that a charge of greater than or equal to 1 is considered large, so they also have a relatively large charge, okay? That's a -1 charge, that's considered a relatively large charge. So we have a small distance, we have big charges, and that means that the bonds are strong, okay? Ionic bonds are strong, and so the melting points, is it going to take a high temperature or a low temperature to break those really strong bonds? It's going to take a really high temperature to break those bonds. And so the melting points are going to be very high because a lot of energy is needed to break those very strong bonds. Okay. A metallic bond. And remember, metallic bonds are between a metal and a metal. They can all be the same type of metal. So you could have pure gold or pure silver, pure copper, or you could have an alloy, which is a mixture of metals. I'm going to write that down one more time here. An alloy is a mixture of different metals. Okay, so here we have some lovely little Bohr diagrams. A metallic bond is formed when several metal atoms shed their extra valence electrons in order to become stable and have an octet. This creates a crystal of metal cations. Okay, here is the metal cation with its empty valence shell. Okay. And the valence electrons, if you recall, they are what we call delocalized. They are not locked in one location. They are free to move. So maybe we have, this guy is moving over here, and this guy is now going to move up here, and this one's going to move down here, and this one's going to move this way, and all of the little valence electrons are moving around. Now, in the meantime, we're going to have some forces here. So we're going to have forces. Let's make that maybe a little green thing for the force. There's going to be a force between that valence electron, which is negative, and the metal cation, that's this thing here, which is positive. So we've got forces between all the valence electrons and the cations. And you can see these are acting like glue, these forces holding the entire thing together. If you were really lucky, you're going to remember that we had that model of a metallic bond where I had that little container and it contained styrofoam balls in corn syrup. And the corn syrup was like the valence electrons because it stuck the styrofoam balls, which were like the metal cations, together. So you can see the green stuff is like the glue, and those are metallic bonds. Okay. Metallic bonds are the force between the metal cations and the free-moving valence electrons. Okay, and metallic bonds are strong because the distances between the cations and the mobile valence electrons are small. So once again, we have a small distance, so which is going to make the force stronger. The amount of charge, we're looking at charges of like either +1 or +2 or +3 for the cation. And all of the electrons have charges of -1, so those charges are considered large. The amount of charge is large, which is also going to make the force large. So the electrostatic force is very large, therefore these are very strong bonds. So you're going to require a lot of energy to break those bonds. And that's going to mean that the melting points are very high. Okay, so ionic bonds, distances are small, charges are big, they're strong. Melting point is high. Metallic bonds, the distances are small, the charges are big, therefore the forces are strong, therefore melting point is high. And finally, we have our covalent bond. Okay, and our covalent bond is formed when we have two nonmetal atoms and they share their valence electrons to form an octet. That octet is that full valence shell. And it's full with 8 electrons, and a group of 8 is called an octet. This creates a stable molecule. And so if a covalent bond is formed, you can either create a molecule of an element, say for example you have H2, that's one H atom bonded to another H atom, or you could create a molecule of a compound, which could be, for example, H2O, where we have two different types of atoms, which makes it a compound. Okay, so how does this hold together? Well, I don't know if you remember, but in the class, we made a covalent bond. There was me, and I would hold my pen as an electron in my hand, and I would have a student hold a pen as their electron in their hand, and my head was my nucleus, and their head was their nucleus, and then we would hold the two pens together between us, each of us with one hand on each pen. So these shared electrons would be like those pens. Whoops, shared. Would be like the pens, and the positive charges, those are the nuclei. And what's holding these bonds together? It's that attraction between the nuclei and those shared electrons. Okay? There's our attraction there between the nuclei and the shared electrons. Covalent bonds are really strong because the distance between the nuclei and the shared electrons is really small. The amount of charge is really large. Hopefully at this point you're getting the idea. If the distance is small and the charge is large, the forces are strong. So the distance is small and the charge, remember charge can be represented by Q. The distance is small, the charge is large, and so the forces are strong. And if the forces are strong, you need a lot of energy to break them. And if you need a lot of energy, that means that your melting point temperature is going to be high. Okay? Now this is where covalent bonds get tricky. So I'm going to actually stop this video for today because that seems like a reasonable amount of time to spend on this. And so let's just review. Ionic bonds require lots of energy to break. Metallic bonds require lots of energy to break. Covalent bonds require lots of energy to break. And why is that? It's because the distance between the charges are small and the charges are large. And here we are going to pause for today. Thanks for being with me. We'll see you next time.